Hello everyone, I am Masood Ibn Abdul Wahid. Today in this video, we are going to see the solution of some Anna University question paper problems. The question paper was the recent one, it is April-May 2023. The topic from which the problems was taken for today's discussion is mesh analysis. So just a brief about mesh analysis. A mesh or a loop, both are the closed path in an electric network. But the difference between loop and a mesh is, loop is nothing but any closed path in an electric circuit can be meant to be a loop. But if it is to be meant as a mesh, there should not be any other closed path inside a mesh. So that is the difference between mesh and a loop. 3 videos back, we have discussed what are the steps we have to do and what is the difference between Kirchhoff's law and mesh analysis while solving a problem we have discussed before in the previous videos. The link of that video I will give it here. So this is the mesh analysis where we are going to assume the loop currents, not the branch currents. If you assume branch currents, it is nothing but the solution based on Kirchhoff's law. After loop currents, we will be concentrating in voltage drop and rise in a resistor or in batteries. With reference to the travel direction, if the loop direction is also aligning with the travel direction, it is potential drop. Whereas if the loop direction and the assumed current direction is opposite, it is called potential rise. In case of batteries, according to the assumed current direction, if the current passes in a battery internally from negative to positive polarity, it is called potential rise. Whereas according to the assumed current direction, if a current goes internally inside a battery from positive to negative polarity, it is called potential drop. So with this 4 logics, we will go into the solution. The question given to us is, determine the current in 4 ohm branch in the given circuit, and they have indicated us to use mesh analysis method. The given circuit is this one. So as you can see here, there are many closed paths. For example, this you can assume to be a closed path, and this you can assume to be a closed path, and this you can assume to be a closed path. Also, you can assume this to be a closed path. So like this, there are many closed paths you can see in the given network. Those are called loops. But what about a mesh? Again, I'm saying mesh is also a closed path of a given electric network where there is no other elementary loops inside. With the reference of this definition, if you see this loop, there is no other closed path inside it. So it is a mesh. In the same way, if you see this, there is no other closed loop inside this. So it is a mesh. In the same way, if you see this closed path, there is no other closed path inside this. So it is a mesh. But whereas the outer closed path, if you see this to be a closed path, this is a loop. It cannot be meant as a mesh because there are 3 other inside elementary loops present in this closed path. So the outer ring or the outer loop cannot be called as a mesh. So now, as we discussed, there are 3 meshes inside. So we will be assuming 3 mesh currents, or you can also call it as, in simple terms, loop currents. So this is one mesh current I1, this is the another mesh current I2, and this is the third mesh current I3. And to write the mesh equation, we need to refer the loop travel direction. So for that, we are in need of naming the nodes available. So let us name the given circuit in terms of nodes like this. We will take the first loop for our travel. We will take the first loop to be loop 1. So loop 1 is A, B, C, D, A. Once again, I am saying whenever you write a travel direction, loop direction, close it. Otherwise, it may not be called as a loop. It is a path for the current, but it is not a closed path. It is a path, but it is not a closed path. So where you are starting the travel, you have to end in the same node. As I have indicated, A, B, C, D, A. So I have started with A and I am ending the travel in A. Like that you also assume and complete the closed path. Now we will travel from A to B. So when you travel from A to B, there is a resistance of 2 ohm according to the loop current. The current in this branch is I1. And when you see the direction of the assumed current, both are same. potential drop of value 2 multiply I1. So minus 2I1. And when you travel from B to C, there is a 12 ohm resistor. And in this resistance, two currents are dealing with. So one is this mesh current I1 and another is this current I2. So both the currents are in the same direction, that is from B to C. And the travel direction is also from B to C. So because of these two currents are in the same direction, what we can do is we can make the current to be I1 plus I2. The current going through this 12 ohm resistance is I1 plus I2. Why the plus comes? Because both the currents are from B to C. And the travel direction is also from B to C. So started with the minus with the value of potential 12 multiply I1 plus I2 as written here. Let us move from C to D, where we are having a 1 ohm resistor. Here also there are two currents dealing with. One is the current I1, another is the current I3. When you check the direction of these two currents, these two are opposite to each other. So the total current in this 1 ohm resistor is I1 minus I3. We are writing the voltage equation of this loop. So let us assume the current I1 is greater than I3. The travel direction is this C to D and the current direction is from C to D. So it is a potential drop. Started with a minus, the potential drop will be 1 multiply I1 minus I3. And when you go from D to A, there is a battery, and according to the assumed current direction, the current internally flows from minus to plus. So it is a potential rise, so plus 12 equal to 0. So this is the mesh voltage equation which is written for this first loop. So you're manipulating this and simplifying this, you can separate out the three current I1, I2, I3 separately and their coefficients separately, and you will end up with this equation which we can note it to be equation number 1. Let us go into the second loop, which is E, B, C, F, E. In this, let us start from E to B. There is a 2 ohm resistor with a current of I2. Both the directions are same, so it is potential drop. And when you travel from B to C, as we discussed, between B and C, there is a 12 ohm resistor where the resistor is having two currents, I1 plus I2. So the travel direction and the current direction are same, so it is again a voltage drop. And when you travel from C to F, there is a 3 ohm resistor and two currents are dealing, I2 and I3, and these two currents are in the same direction. So the current through 3 ohm resistance will be I2 plus I3, and the travel direction is aligning with the current direction, so it is again potential drop. Minus 3 of I2 plus I3, and travel from F to E, there is a battery. According to the assumed current direction, the current flow internally is from minus to plus. It is a potential rise of 10 volt, which is equal to 0. Manipulating and simplifying the written equation, you will end up here, which is equation number 2. And in the loop 3, let us travel from D, C, F, G, H, I, D. So when you travel from D to C, there is a 1 ohm resistor for which there are two values of current I1 and I3 which are of opposite signs. So again I am saying, now we are writing the equation for the third loop, that is for the third mesh. So assume I3 is greater than I1. So in that case, since these two are opposite, the current through the 1 ohm is I3 minus I1. Don't write it as I1 minus I3. It should be I3 minus I1. Okay, so since the travel direction and the current direction are same, it is a potential drop which is of minus 1 I3 minus I1. And from C to F, again there is a 3 ohm resistor. The 3 ohm resistor carries two currents I2 and I3 in the same direction, so it is I2 plus I3. As the travel direction and the assumed current direction are same, here also it is potential drop, minus 3 I2 plus I3. And when you travel from F to G, there is nothing, and when you travel from G to H, there is a 4 ohm resistor, and according to the current direction and the loop direction, both are same, so it is potential drop minus 4 I3. And when you travel from the node H to I, there is a battery of 24 volt in which, according to the current assumed, the current is going from negative to positive, so it is a potential drop plus 24 equal to 0. Manipulating and simplifying this equation, we will get the equation number 3 as shown to you. So now we have 3 mesh currents and we have 3 voltage equations. By solving these 3 equations, we will get the individual current of the meshes, namely I1, I2, I3. So these equations are written with some logics. Instead, the same equations you can form just by seeing the network without any voltage equation. How? By using the Cramer's rule. So this method is also called as inspection method of writing equation. Why it is called inspection method is just we are going to inspect the given network with the current assumed, and we are going to straight away write the equation. So this Cramer's rule is written in terms of matrices, so where we will have 3 matrices. Resistance matrix multiply current matrix is equal to voltage matrix, nothing but Ohm's law. V is equal to I into R. The dimension of a resistance matrix will be n cross n, and the dimension of current matrix will be n cross 1, and the dimension of voltage matrix will be n cross 1, where n is number of the mesh available in the given network. And what are the individual elements? So the resistance matrix will have 3 rows and 3 columns for the given network because it is having 3 loops. So we will be having 9 elements in the resistance matrix, R11, R12 up to R33, where this diagonal elements R11, R22, R33 are the summation of the resistances in the respective mesh or in the respective loop. For example, R11, it is nothing but the summation of the resistance values available in first loop, and R22, the summation of the resistances available in the second loop, and R33, the summation of the resistances available in the third loop. And what about the other terms? R12, it is the common resistance available between the loop 1 and loop 2. And R13, it is the common resistance available between loop 1 and loop 3. R21, it is the common resistance available between loop 2 and loop 1. And R23, it is the common resistance available between the second loop and the third loop. Again, R31, which is equal to R13, R32, which is equal to R23. So like this, we have to calculate the resistances of individual elements. And I1, I2, I3, these are the unknown values. And V1, the total voltage available in the first loop. V2, the total voltage available in the second loop. V3, the total voltage available in the third loop. So like this, we have to form the resistance matrix element values, and we have to find the voltage matrix element values. Now let us cross check this. R11, which is the summation of resistances connected in first loop. So 2 plus 12, 14 plus 1, 15. So 15 is the element value R11. So 15 is written here. And R12, which is the common resistance available between first and second loop, it is 12 with a sign of positive. Why the sign is positive means I1 and I2 are going in the same direction, so it is positive. So plus 12. And R13, the common resistance available between first and second loop, it is 1 ohm. So it is written as minus 1 because the current direction says that I1 is opposite to I3. So since these two currents are opposite, we are writing it as a negative term, minus 1. And R21, which is equal to R12, and R22, the summation of the resistances connected in loop 2. So 2 plus 12, 14 plus 3, 17. So it is written 17. And 3, R2, 3, which is the common resistance available between the second and third loop. It is 3 ohm. It is written to be positive 3. Why? Because the currents I2 and I3 are flowing in the same direction. So it is positive 3. And R31, which is equal to R13, R32, which is equal to R23. And the last element R33, the summation of the resistances connected in loop 3. So it is 1 plus 3, 4, 4 plus 4, 8. I1, I2, I3 are the unknown current values, and the voltage available in the first loop is 12 volt. There is no other battery in the first loop, so 12. And the voltage available in the second loop, it is 10, and the voltage available in the third loop, it is 24. So all the battery voltages are written to be positive because according to the assumed current direction, in all the three batteries, the current is internally flowing from negative to positive polarity. Now when you multiply these individual elements, you will end up with this equation. For cross checking, you can do one at a time. So 15 multiply I1 plus 12 multiply I2 plus minus of 1 multiply I3 equal to 12. So you will see the equation here. You can write the values of this matrix just by inspection method, or you can write the voltage full equations by using the logics what we have discussed previous. Which method is convenient for you, you can use that and you can go to the answer quickly. So you can take these three equations or you can take this matrix and you can go to the solution. When you take this matrix, the current I1 will be calculated as del 1 by del, I2 will be calculated as del 2 by del, and I3 will be calculated as del 3 by del, where del is the determinant value of this resistance matrix. Del 1 is the value of this, is the determinant value of this matrix by replacing the first row with the voltage matrix, and del 2 is the determinant value of this resistance matrix after replacing the second row with the voltage matrix, and del 3 will be the determinant of this resistance matrix after replacing the third row by the voltage matrix. So like that you can find del 1, del 2, del 3, and after that you can end up with I1, I2, I3. Or you can just have the equation and you can use the calculator to solve these three equations to get the required answer. As of now, these are the three equations which we have written and cross-checked in both the methods, that is by using voltage equation method and by using Cramer's or inspection method. You can solve these three equations by using the calculator in equation mode, and the number of unknowns what you have to choose is 3. And give the coefficients of each equations I1, I2, I3, and when you solve in the calculator you can find the answer of I1, I2, I3 to be indicated as here. The value of I1 is 2.72, the value of I2 is minus 2.057, and the value of I3 is 4.11. So one thing to be again noted is I2, we got the equation in terms of minus value, so it indicates that the actual current of I2 is in the opposite direction to the assumed one. So that is the reason why a minus is resulting in the answer. Okay, now the required current to find in the question is the current through 4 ohm resistor, and it is nothing but I3, which is 4.11 amps. As usual, we will plot the same circuit in Proteus and check what is the current actually flowing in the 4 ohm resistor. So to reduce the length of the video, I have already drawn the circuit with only one insertion, that all the loops is having an ammeter inserted to read out the currents I1, I2, I3, and just run the simulation. So this is the loop current 1 I1, and this is the second mesh current, this is the second loop current I2, which is read to be minus. In the manual calculation also we encountered this minus, and the loop 3 is having a current of positive 4.11, which is the current through this 4 ohm resistor. And with this we can conclude that the manual calculation is correlating with the Proteus simulated answers. So we have manually calculated the current through 4 ohm resistance to be 4.11 amps, and using the Proteus simulation we have correlated the answer, we have cross-checked it. And so far in this video we have taken a problem from the analytic question paper related to mesh analysis topic, and we have solved the problem manually. Also we have correlated the answer with the Proteus simulation answer. So thanks for watching. So we will meet in the next video with some other problems in another topic. Until then, I am Masood Ibn Abdul Wahid signing off.